今日は利根倉、奥利根ですよ。今日は奥利根。奥利根なんか初めて聞いた。
What you're asking for is, if you know that this is continuous and that is R continuous, can you prove from these two that this is continuous in the original sense? And the answer is yes, you can. It's two lines. So indeed, because with differentiability it's an accident of topology that I can decide it at this level in the first place. Hence, I de-emphasize this point. With differentiability, I have no differentiability at the manifold level to compare with. That's the question you asked. How does it compare to the original notion of continuity? But for other notions, I do not even have something to compare with, and then you're thrown back to the manifold and to the chart picture, and then world definition is all you that remains to be cared of. Thank you.
You need to get something that is invertible and the inverse is continuous.
In here, you... I'm not sure. It could be. Let me think about it. It could be that you're right. That you need the continuity of the inversion as well in order to do the red invitation arrow. It could be. I think not, but I'm not sure. It's simple. We do this in the break. Okay. Please, another question? Okay, if there are no further questions, I invite you to the tutorial at 2 o'clock. Yes.
This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Good morning, welcome back to the third lecture. Today's lecture is lecture 3, Multilinear Algebra. And the essential element of, or the object of study of multilinear algebra is just vector spaces. However, a word of warning from the beginning, we will not equip space, or later space-time, physical space or space-time, with a vector space structure. You might think we would, because before we had a set and we equipped it with a topological structure, with a topology, and in fact that is one step towards the picture of space-time. Now today we'll talk about, and in this lecture we'll talk about equipping a set with a vector space structure, but if this doesn't further our aim of describing space-time, why do we do it? And it doesn't further this aim, and I emphasize this only because often it is assumed that space, physical space, or physical space-time carries a vector space structure, and I do not want to enter into the discussions now, but my question would be, if physical space-time, the positions, carried a vector space structure, then you should know, or the other question, or do you know, where 5 times Paris lies? Where is 5 times Paris? Does that make any sense? Or where does Paris plus Vienna lie? There is no such notion on physical position space to add places, to add positions, or to multiply them by real numbers. So we will not equip space-time with a vector space structure. So however, why do we look into this? The tangent spaces, and that's a notion that is deceptively intuitive, but in fact, bear with me until we define it precisely, but the tangent spaces that have the name TPM2, a type of manifold we're going to discuss in the fourth lecture today, to smooth manifolds. So TPM will be constructed in lecture 5 on Friday, and these are objects that can be written down for smooth manifolds, and smooth manifolds will be defined in lecture 4 today. The tangent space to smooth manifolds, very roughly, so you can think of them, but in fact we will define them differently. If this is the real world, say a sphere, then you could for instance think of the tangent space attached to the North Pole, P, which is a CPM, but you could at any other point of your real world, you could attach another point Q, you have another tangent point here, and on the sphere you have many different tangent spaces. In fact, we won't define them in this way, it will be defined slightly differently, but the point is, whatever way you define them, these guys, they carry a vector space structure. And the natural one at that. So even though the underlying position space, space-time, does not carry a natural vector space structure, the tangent spaces do. And the tangent spaces, once you have them, you have a vector space here, you have a derived notion there, that's the notion of a tensor. And tensors are very important in differential geometry, and it's best to first understand them abstractly. So the advantage, or it's beneficial, to first study vector spaces and all that comes with it abstractly. So we could enter immediately into studying these concrete vector spaces, but the point is, this is for two reasons. It's better to have this lecture 3 as we have it today. The first reason is, even in the exact construction of the TPM, for construction of TPM, which will be a finite dimensional vector space, or this will be defined, one needs an intermediate vector space, which is again a vector space, which is called P infinity M, whatever that will be. And so you cannot even construct this guy without understanding previously what vector spaces are abstractly. So it is worthwhile doing that. And the second is that tensors, or tensor techniques, so the definition and what you do with them, tensor techniques. Understood. In an abstract setting, where you don't have to worry about this specific vector space and its details, but tensors are something that are defined on any vector space, are most easily understood in an abstract context, or an abstract setting. This is the reason why, for a moment, we leave our aim where it is, but consider multilinear algebra. So, first section is vector spaces. As I said, vector spaces are the object that is being studied in linear algebra, and you certainly saw the definition, nevertheless let me repeat it. The definition is a vector space is a triple consisting of a set and two operations plus and times, so where a vector space is, first of all, a set V, and I don't call it M because it's not the M we had before we're going to include with the vector space structure. Later on, so if you later on want to identify this V we're now talking about will, for most of the rest of the course, be a 2pm at a certain point, or at another point. Okay, that's where we're going to apply it. Second, you have a so-called addition. And what is an addition? An addition is a map. Why? Because it takes two vectors and it maps them to a vector. If you have such a rule, you have an addition. And the third element is you have an S multiplication. It's not a multiplication, it's an S multiplication. What does that mean? That, okay, I should take a real vector space, an R vector space, and this S multiplication.
あ、どうも。いや、どうも。ちょうどマックでちょっと乗ってもらってください。今、ごめんなさい、オートですけどね。あ、どうも。ちょっとお待ちください、すぐ来ます。はい。Maybe it's worthwhile marking them in red
supposed to be from the real numbers. And you see here, this is the times on the vector space, because the real number times the vector, that's this guy. The result is a vector, so I again have to multiply it by a real number. But this times here, this is the multiplication on the real numbers. And that's a different thing. So we use the dot in both cases, but it's useful to use colors at the moment, okay? Then there are two distributive laws, lambda plus mu times v equals lambda d plus mu v. Okay, this is of course on the vector space, this is between real numbers. This is on the vector space, and this is on the vector space. And there's another distributive law, namely lambda times e plus mu times, no, plus lambda times w. Again, vector space equals lambda times v plus w. Vector space, okay? And the unitary law looks a little trivial, but it's important. 1 times v is again v, and that's of course this, and this is the 1 from the real numbers, okay? So any structure of this type that satisfies these axioms is vector space. Now, a word of terminology, a vector is an element, I formulate this differently, an element of a vector space is often referred to, and I emphasize informally, as a vector. So you must not ask the question, what is a vector? Well, you can, and I'll say it's an element of a vector space, but the question is, if I put you one vector there, I put one here, however I do this, and I ask you, is it a vector or not? The point is you don't know. I make this remark in a second again, and you'll understand what I mean. Now, of course, you all have in your mind R to the 3 as an example, a prime example of a vector space. And R3 can be made into a vector space. It's not a vector space all by itself. And last night when we decided what examples to present in today's lecture, we looked in Machiavelli's book, The Prince again, and there he says you have to do the cruel things in the beginning. Now the cruel thing I'm going to do, I will not give you a single directly intuitive example that makes contact to what you know about vector spaces. Why don't I do that? Because you will probably imagine more than what I write down. I don't want that. I will give you an example for just everything we construct today, which are perfect examples, but which are not quite immediately, unless you're a mathematician, make you think, oh, that's what I always thought what vectors are. But that will force you to sharpen your understanding of the definitions. Okay? That's it. And in the tutorials, you then will be reconciled with the abstract notion, and Rn appears at some point. So the one example I will employ again and again for all constructions is the following. I first define the set. P, that's what I call it. It's the set of all maps, small p, with a big P, or small p, from the real interval -1 to +1 into the real numbers. But not just any of those. I just looked at those as a map can be written as sum n equals 0 to some capital N with some coefficients, call them n, so they are from the real numbers, times x to the n. Or in other words, this is the set of polynomials of, let's say, 6 n, capital N equals 7, 6 degree. Times this part of the real line. X squared, for instance, or 2 plus x to the 7 if n is greater than 7. Okay? It's a collection of such objects, a collection of functions, of polynomials. You ask, is this a vector? And it depends on whether in the background you define this or not. However, if somebody insists this is a vector, but cannot tell you how to add it to another vector, another element of the space, then he or she is in trouble. So in a sense you can say, are these two things vectors? Well, if you can't add them, you're in bad shape. Okay, but you see, it's a bad question actually, because being an element of something only refers to the underlying, so as we could write T plus times is a vector space, and of course one has to check the exact things, and I'm sure you can, I'm sure that's easy. T plus times is a vector space, but if you say a vector is an element of a vector space, that's fine, let this die, it only refers to the underlying set, so somehow it's not a good question, is something a vector? But you can certainly talk about vector space. That's all I want to say, because in relativity there's often a question, what is a tensor? What is it? And a vector is a special type of tensor. Well, how do you say something is a tensor? You don't, you can only define tensor spaces, and you make informal element tensors. That's my point, okay? I rather want to discourage you, this word informally, from using the terminology at all. Of course, I myself will not adhere to this advice. Okay, so this was the first question so far. Well, the same would be a ring in a space instead of a vector, but apart from that, sorry, question. So the question was, how I would rephrase the statement in quantum mechanics, that quantum mechanical space is an element of a vector in the Hilbert space, I would say it's an element of the Hilbert space, although a state, a quantum mechanical state is a ray in the Hilbert space, not a vector itself, because there's ambiguity with the phase and the law, okay? But it would say it's an element of the Hilbert space. Why would I have to say to call it a vector? Okay, sure. Now, linear maps. It's a standard procedure in mathematics. Once you have an object defined, a structure, a space with certain structure, that you investigate the structure by considering maps between one such structure and another instance of such a structure. We do this in topology, between one topological space and another topological space, and we study maps between them which preserve or respected the structure. In topology it was the open set structure. Two images of open sets are open. Here, if you want to follow this general philosophy of studying structures by studying structure respecting maps, you need to look at so-called linear maps. So these are the structure respecting maps between vector spaces. You ask, why would I look at structure respecting maps? The answer is this is always a good idea to learn more at any structural level. So we do this here. And that's just called constitutional called linear maps. So if E plus S multiplication to vector space, and I write plus E and plus S multiplication E, the additional S multiplication V, and W plus on W and S multiplication on W, these have nothing to do with each other, right? Then these two vector spaces, any two vector spaces you like, then a map phi from E to W. You see the map, again, only refers to the underlying set, because if you know how one element goes to the other, you have that, then a map is called linear. If two conditions are satisfied, the first one is phi of V plus V0 is phi of V plus